Hello students. So today we are going to start a fresh new chapter, and the chapter name is, guys, simple harmonic motion. Okay, simple harmonic motion. So this chapter, guys, we are going to start, and in the recent changes that has been happened in the JEE advanced syllabus, if I talk about, there are these two more topics that has been added in that is damped oscillation and the forced oscillations. So guys, we are going to cover those topics also at an advanced level. Okay, earlier it was only the part of the JEE mains, but now it has been added to the JEE advanced also. So we will go up to the level of problems, the level of concept that is needed in the JEE advanced. Okay, so okay, so we'll start this chapter. The chapter name chapter as a name, it is known as what, guys? Simple harmonic motion in general in the in the coaching industry. Okay, but if I talk about, it is basically the oscillatory motion that we are going to see. Okay, so oscillatory motions that we are going to see as a chapter. Okay, because now we are not only focusing on the simple harmonic motion, we are focusing on the damped oscillations also, forced oscillations also. Okay, so that's why the spectrum becomes bigger now. So that's why the chapter more suited as a name should be what, oscillatory motion. But nevertheless, for right now, guys, let's start with the simple harmonic motion only. Okay. So before, guys, we start in the detailings of everything, there are few, you can say, the basic definitions we should understand first. Okay, so before we are going to begin this, guys, we should understand few more, few basic stuff about this oscillatory motion. Okay, so guys, the first thing that we have to see is what is periodic motion. Okay, so the first thing, guys, that we are going to understand is what is periodic motion. Okay, so we'll go slowly, guys. Okay, we'll cover every the fundamental definitions and the details, and then slowly we will build up this whole chapter. Okay, so guys, the periodic motion. So if I talk about what is periodic motion, guys, I can say like this, that if I write, I would say, guys, the motion of a body or a particle which is which is repeated which is repeated after a given given time interval is called periodic motion is called periodic motion. Okay, guys, so this is a very basic definition of what, guys, of the idea of periodic motion. Means, suppose, guys, if we take a, let's say, this circle. Okay, and there is a particle, okay, which is here we are having. And now this particle, if we take, just a minute, yes, I'll try to create this. Yes, now I think we can do this animation, because if you see, if this particle is moving uniformly on this circle, okay, uniformly on this circle, so we know that after every a certain time interval it will repeats its position again. Okay, means, let's say, if I say this is the position, okay, and this is the position of the particle, this is the position of the particle, guys, O. So it is going to repeat this position after every constant time interval, if it is moving with a, what, guys, a uniform angular velocity or a constant speed. Okay, so if this is the case, we can say that it is doing a what, periodic motion. Okay, it is performing a periodic motion. if we see guys that let's say this is our sun, okay, and this is our earth. So guys, earth is revolving around the what sun, and it is taking around 365 days to cover this, okay. So on average we can say that it is also doing a sort of periodic motion only, okay. And if you talk about the earth only guys, okay, if you see, earth is also revolving about its axis, okay, revolving about its axis with some angular velocity, so that it is doing a complete one rotation in what guys, in 24 hours. So it is also guys an example of what, a periodic motion. So something guys, some sort of motion which is repeating itself again and again itself after a certain time interval is known as guys what, periodic motion, okay, is known as what, periodic motion, okay. So I hope this idea would be settled for you guys, okay. So now after this we will move to the next definition guys, that is known as what, oscillatory motion, okay. So guys, the next thing that we have to understand is what is oscillatory motion. What is guys what, oscillatory motion. So let me write down the definition first for you, and then we can discuss a little bit about that, okay. So guys, an oscillatory motion, an oscillatory motion is a type of motion in which particle moves to and fro to and fro about a fixed point, about a fixed point fixed point known as also known as mean position with the help of any restoring force. Okay guys, so this is the idea of what guys, an oscillatory motion, okay. It is an idea of what guys, oscillatory motion. To understand this thing guys, I'll take some examples for you. So suppose guys, if we make a like this simple pendulum, okay, simple pendulum. So guys, this is a particle. So if I take it, bring it here somewhere, so guys, what it will do, it will go like this, okay, it will go like this. And guys, if you see here, it will perform this kind of motion, okay, this kind of motion it will be performing, okay. So this kind of motion guys, it is going to perform, okay. And if air is available guys, okay, air drag would be available, so guys, this motion will turn out something like this, and then guys, it will stop. So guys, it is an oscillatory motion only, okay, oscillatory motion. But guys, if you see, after every oscillation, the size of the extremities is getting what guys, reduced, okay. The size of extremities are getting reduced, and it is coming back to what guys, mean position. So this is guys known as damping, okay, that we will see later. But guys, this is also an example of what, oscillatory motion. If let's say guys, there is no air, total vacuum is there, there is no air resistance, nothing is there guys, then in that case it will do this kind of a motion only for a indefinite time, okay. For indefinite time it will be performing this kind of a motion, okay guys. One more example that we can take, let's say, to show you is guys, suppose if we have this kind of a sphere, let's say, and it is resting on a ground, okay. And suppose we have this kind of spring, which is what guys, connected to the top of this, and let's say the radius of this is what guys, r. And here guys, sufficient friction is available, sufficient friction is available to stop slipping stop slipping. In that case guys, suppose if what we do, we give this body a little bit, what we pull off this side, okay. So what will happen guys, it will go like this, okay, a little bit extension will happen here, okay, and this will become like this. And then guys, what will happen, this body will start oscillating guys, okay, it will start oscillating like this way, okay, it will start oscillating like this way. It will make some angle like this, and then it will make some angle like this. So guys, it will start oscillating like this, okay. I hope you are able to visualize this thing, that what I am trying to say, okay. So guys, this is also what an example of what oscillatory motion, and of course this would be what guys, its mean position at that instant, okay, because here the spring is at its natural length, and body will be what guys, in equilibrium. Now if you displace it guys here, so what it will do, the spring will pull it back, and when it pull it back guys, spring is going to get compressed because of the inertia, and then it will push it back. So this kind of a oscillatory motion is going to happen guys. The sphere will from the bottom will not move, only it will move like this, okay. So guys, that's this is also an example of what guys, oscillatory motion, okay. So I hope you understood guys this. Now coming to one important note point guys, we can say, is this, that see, the thing is, I'll give this note to you. The note is guys, what the note is, that all the oscillatory motion guys, okay, all the oscillatory motion, oscillatory motions could be, could be a periodic motion, could be a periodic motion, if there is no damping or anything is happening guys, okay. If there is no damping is happening, then we can say of course all the oscillatory motions are guys, what could be a periodic motion, okay, because they are repeating themselves after a definite time interval. So guys, all oscillatory motions could be a periodic motion, but not all the periodic motions, periodic motions are oscillatory motions, okay. Because if you see guys, if we talk about the earth here, okay, earth revolving around this sun, guys, there is no mean position of the earth where it is trying to come back, okay, and there is no restoring force which is acting on the earth, which is trying to bring this body to back to this position guys, okay. So this is not a, you can say, what we can say is a oscillatory motion. It is just a simply guys, what a periodic motion. If you talk about earth revolving about its own axis guys, it is also a what, a periodic motion, but not an oscillatory motion, because there is no restoring force, nothing is there here guys, okay. A particle moving on a circle guys, which is similar to this case only, is also guys, what a only periodic motion, but not oscillatory motion. If you see guys here, in these cases, as I have talked, but I'm just I think I haven't elaborated this precisely, so I'll elaborate this again guys. If you see here, this is tension that acting, okay, and if let's say this is theta guys, this is mg, so guys this will be also what, theta, we can say this will be what, mg cos theta, and this will be what guys, mg sin theta. So if you see guys, there is a force which is trying to bring this body towards what guys, this mean position, okay, this mean position or the fixed point. And that's why guys, it is known as what, restoring force. When the body will go this side, then guys what will happen, this side the force would be acting, okay. So if you see, the force is changing its nature depending on that which side the particle is right now, okay. So that's why it is known as what guys, restoring force. I hope you understood. So guys, this kind of a restoring force should be available in the oscillatory motion. If it is not, then it is not a oscillatory motion, it is might be only periodic motion, but not an oscillatory motion, okay guys. So I hope you understood this idea also very clearly, okay guys. So now coming to the some next few basic definitions guys, okay. So the next thing that we want to talk about is what guys, the types of oscillatory motion, okay. So guys, the next thing that I want to talk about is types of oscillatory motion, okay. types of oscillatory motion. So guys, primarily there are three classifications that we can do. So let me write those. So guys, the first one is basically the free oscillations. Okay, free oscillations. Second one we can say as a damped oscillations, and the third one is guys forced oscillation. Okay, forced oscillations. So these are the guys what three uh, like primary classifications of oscillatory motion guys, what we can say. So let me briefly introduce you all these three variations, and then we will see this free oscillation in detail. Okay guys, so let me write down guys these three first. So free oscillation guys, the first one that we want to talk about is what is free oscillation. What is free oscillation? Okay, so guys, if you see here, uh, I'll write like this way. The definition guys of this would be free oscillations. Free oscillations are those in which once oscillation of a particle starts, it continues for a indefinite time, for a indefinite time, till some external force, some external force, some external resistive force, we can say some external resistive force appears in the opposition to the appears in the opposition to the restoring force, restoring force acting on it, acting on it. Okay guys, so it's a very simple idea guys. If you see, like, let's say if we have a, what we can say, let's say this is a body, okay, and this is mass m. Let's say guys, if I displace this particle by a x distance, okay, and then I leave it guys, then what is going to happen, it will move like this guys. Okay, this is the kind of movement it is going to perform. If guys, if you see this as a system, if you see as a system guys, in this system, this spring force and this what we can say, the block is there, mg and normal are what guys, balance, and there is no other external forces are acting guys, and mg and normal is guys what, balanced, and they are not doing any work, okay, on this system. And of course here normal force is there, okay, reaction forces would be there, but they are also not doing guys any work. So what we can say, the system energy should be what guys, reserved. Okay, the system energy should be what guys, reserved, because there is no external work done is happening guys. So spring plus block as a system, there should be no energy going to be lost if there is no other forces are acting. So guys, if I leave it from here, it will do this kind of SHM for an indefinite time. Okay, it will do this kind of SHM for indefinite time till any resistive force guys. Let's say if here guys, what is going to happen, if you see, if I put air molecules here, okay, I'll put air molecules are here. So guys, what is going to happen now, when this particle will try to go guys this side, okay, then air will apply the air drag force like this way. So there is some negative work done is happening guys, okay, which is a form of frictional force, which will take the energy from the system in the form of what guys, is a heat loss and the sound energy loss. And when it will go back this side guys, then this time guys, the force will act in this direction again, okay, and what will happen guys, it will take the energy again from the system, and when it is coming back this side guys, okay, then the restoring sorry, the resistive force will act in this direction, and again it will lose the energy. So for every event guys, every part of the oscillation, the energy is going to be lost due to the frictional interaction, you can say, between the block and the air molecules. Okay, and because of that guys, the system is going to lose the energy, and at the end it will going to be stopped. Okay, but if let's say this kind of a problem is not there, it will be doing this oscillation for an indefinite time. Okay, it is not going to stop at all. So guys, that kind of oscillation where this kind of a resistive force is not available at all, which is practically, I think it's almost impossible to do so, to achieve so. But like guys, if we are able to pull it off, it will do for an indefinite time guys, the oscillation. Okay, but if it is not there guys, then it will get damped and it will stop. So guys, if this kind of a resistive force is not there, we will say this oscillation is known as what? Free oscillations. I hope you understood guys. Okay, now coming to the next idea guys, that is what is a damped oscillation. Okay, what is damped oscillation? So guys, let me talk about what is damped oscillation. So damped oscillation, second thing is what guys? Damped oscillation. Okay, damped oscillation. So what is damped oscillation guys? Here I can write what is damped oscillation, that damped oscillation are those in which when a particle start its oscillation, particle starts its oscillatory motion, let's say oscillatory motion, due to friction or some other naturally opposing forces, the oscillation amplitude of particle start decreasing with the time, starts decreasing with the time. This is called damped oscillation. Okay guys, so I hope this is you have understood already. Okay, so I'm not going to explain it again. Okay, we have talked above only guys, that what is the damped oscillation. When the air is interacting with the particle guys, okay, when the air is interacting here guys with the particle, it is taking out the energy from the system, and the system will what guys, do this kind of a thing, like this kind of oscillation, and it will stop. Okay, so that is guys known as what? Damped oscillation. And coming to the last one guys, that is what? Forced oscillation. So let me explain that also for you. The forced oscillation guys, forced oscillation. Okay, so forced oscillation guys, how do we explain this? If you see, forced oscillations are those in which damping is not allowed by applying an external time varying force on the particle particle which compensate the the effect of damping force damping force acting on it damping force acting on it. Thus it is similar to free oscillation, but naturally the oscillations are damped. Okay guys, so here try to understand guys what I'm trying to say. Let's say if this this block, if you see guys, okay, this block, this is, if air is available guys, it will do this kind of damping and it will stop. So guys, if anyway we are able to achieve this thing, that this force which is acting at every moment on this body guys, when let's say it is going this direction and the drag force is acting in this direction guys, let's say if this is the magnitude of the drag force, if we can apply the same amount of force in this direction guys, so this will what, this will counter this force. Okay, so the net force, the net effect of the damping would be what guys, is going to be nullified. Okay, so it is just behaving like a what guys, a normal free oscillation, SHM, oh sorry, free oscillation. Okay, so what we can say in that case, that it is behaving like a free oscillation, but naturally it is a damped oscillation, but with the help of what guys, some sort of force insertion in the system, we are able to make this system to behave like as a what, free oscillation. So what I say guys in general about the force oscillation is like this, is that it is guys like this. If you see, if I write like damped oscillation plus force is equal to what, free oscillation. Okay, so guys, there is a damped oscillation is going to happen. That damped oscillation, with the help of some sort of force adding to the system, we are able to achieve a free oscillation. Okay, so if that is happening guys, it is known as what, free oscillation. I hope this is settled for you also guys. Okay, so that is the idea of what is the types of oscillations that we can have. Okay, now the next thing guys that we have to understand, which is our main segment of this chapter, that is what guys, what is simple harmonic motion. Okay, so let me write down guys for you. The thing is that we are going to address now is what guys, is simple harmonic motion. Okay, so guys, now we are going to see what is simple harmonic motion. Okay, so guys, if I put this qualitatively, okay, if I put this qualitatively, what I generally say to the students is that it is the simplest possible form of a free oscillation. Okay, it is the simplest possible form of what, free oscillation, and it should follow guys a certain mathematical like condition. Okay, mathematical condition is there that it should follow. If any oscillatory motion which is following this particular mathematical condition, it will be considered as guys what, as a simple harmonic motion. So if I qualitatively say guys, put this, so I'll say like this, that it is the simplest possible form of form of form of oscillatory motion form of oscillatory motion. It is the simplest possible form of oscillatory motion. In bracket guys, of course, it is a for free oscillation only, not for any other type. for free oscillation we are talking about this. Okay, so it is the simplest possible form of oscillatory motion, but the specific case of that is what is free oscillation. So we can say in other words that it is the simplest possible form of free oscillation. Okay, and any free oscillation any free oscillation which follow the below relation can be or will be considered as that it is performing SHM. Okay, and what is this mathematical relation, guys? Is this that it should be follow this d square x by dt square is equal to minus of omega square of x minus x naught, guys. Okay, so here if you see, guys, this omega and x naught is a constant. X is basically, guys, same 1 minute, guys. I'll put this in a better way. Okay, so I'll say like this, guys, will be considered as it's performing SHM if if its acceleration is directly proportional to negative of displacement of the particle from mean position. That's it, guys. Okay, displacement of the particle from the mean position. So acceleration of the particle should be, guys, directly proportional to what? Negative of what? Displacement of the particle from the mean position. So guys, if I put this in a mathematical way, what I can write is, guys, A should be equal to, of course, that is what? The second order differentiation of the position. Okay, and not position, basically the displacement only, but because the initial position doesn't change with the time, so it becomes, guys, what? Directly the rate of change of position only. Okay, so guys, A is equal to what? D square x by dt square, and that should be equal to what, guys? Some 1 minute, some proportionality constant, guys, into minus of x minus x naught, guys, which is what? Your displacement. Okay, where x naught is what, guys? The initial position, which is your mean position. Okay, that mean position we have said as what, guys? X naught. Okay, so if I write this, guys, in a proper way, I can say it is equal to d square x by dt square is equal to what, guys? Minus of omega square x minus x naught. Okay, so guys, this is the equation that the particle should follow if we have to consider it as a simple harmonic motion. Here omega square is a proportionality constant, proportionality constant. Okay, okay, and x naught is the is the is the position of equilibrium point from the origin. Okay, guys, so this is what, guys, a definition of what? The simple harmonic motion. Okay, now, guys, see, the thing is, this definition is only helpful to analyze the linear SHM. Means, guys, the particles which are only doing what? The translatory motion and performing an free oscillation can analyze by this guys. Okay, so I'll just put a remark here guys for you. Okay, so if you see guys here, I'll put a remark for you guys here. The remark is, what guys? The remark is, let me put this clearly guys, remark. Okay, remark, this equation is only helpful for analyzing the particles which are doing only translatory oscillation. Okay, translatory oscillation, also known as what is linear SHM. Okay, linear SHM. Then guys, we can use this equation, but we have seen that there is an example that I have taken guys. Here if you see, I have shown you that this particle is what guys, it is actually rotating guys. If you see, this particle is actually rotating about this axis like this. Okay, so guys, there is a torque is getting involved, and there is guys of course some, this is totally guys a rotatory motion, you can say. Okay, it's purely guys what, rotatory motion. So if it is a rotatory motion guys, then this kind of a linear equation is not going to help us to analyze this SHM. Okay, so of course we should evolve this equation as per that kind of a requirement also. Okay, so for that, if you see guys, I can write another part, that is what guys, that is uh, angular acceleration, angular acceleration angular acceleration angular acceleration should be directly proportional to negative of angular displacement, angular displacement from the mean position, from the mean position. Okay, so guys, if I put this also in a mathematical way, what I can say is that alpha should be equal to d square theta by dt square should be equal to what guys, minus of omega square theta minus theta naught. Okay, so guys, that would be the equation which is going to help us to analyze the uh, like oscillatory motion, which is happening in a kind of those kind of a motion where the rotations are getting involved. Okay, so guys, here theta naught is the mean position, coordinate from origin. Okay, mean position coordinate from origin, and of course omega is a constant. Okay, and guys, if I put the remark for this one, so the remark will be this only guys, that this equation will enable us to analyze the oscillatory motion performed by performed by performed by the objects or particles which are doing either pure rotation or CTRM motion. Okay guys, so if it is someone is doing CTRM motion or the pure rotation, then guys, this equation will be going to help us for analyzing those kind of simple harmonic motion. So guys, that's it for today. Okay, I have just discussed very fundamental basic definitions, and I have discussed the condition, that is needed to express that this particular motion can be studies under the umbrella of what, guys? The simple harmonic motion. And in that also, guys, I have told you the both the possibilities, or which kind of emotions might be we encounter in the discussion. Okay, so guys, that's it. Tomorrow we will continue further. Okay, thank you so much.